Hello Year 11. So, welcome to a video partly based from the physics labs. And I've come in today to show you this wonderful piece of apparatus and to explain to you how we can use it to investigate the behaviour of certain objects under certain conditions. Now, you might be aware of the problem we have when we investigate objects moving. We have a problem that they stop, and they stop because of the force of friction. So whenever we move something across a surface, friction always acts to basically stop it doing that, and that causes a problem. So that caused, so the Greeks never really had a good view of motion because they didn't really get the idea of friction, and also things like air resistance and so on. It didn't make a lot of sense to them. So what we want to do is to have a device like this, which enables us to remove friction. And this long tube, I'm going to give you a bit of a sense at the end, is basically a bit like an air hockey table. So we have a sort of a pump, an air pump, that pumps through, and on top of the tube are tiny little holes. And so air comes up through the holes, much like an air hockey table, removing friction. If you ever played air hockey, you know that that means that things will move for a lot further. So I'm going to start off with one of my little trolleys. I'm going to place it here, and I'm going to turn the pump on. Now, what you'll notice is it started to drift in one direction, because as long as it takes me, it's really hard to get this to balance perfectly. But if I give it a push in one direction, what it will do is it's going to bounce, and it's going to go back again. And there it goes. And this is because at each end is a little elastic band, so it bounces into the elastic band, just moves back and forward. This is an example of Newton's first law, that an object in motion will just carry on doing what it was doing originally, unless acted on by an overall force. It moves back and forward because we've largely removed air resistance. We've removed friction. Air resistance is still an issue, so it will slow down eventually, as is the slight tilt on this, which means it again won't be perfect. But it will just keep moving. Yeah, it's slowing down a little bit now, but it's as good as we can kind of get it. Now, as fun as that is, the reason that I brought this out is because I want to investigate what happens when one object collides with another object, a collision. And the idea of, can I predict what the speed of something will be after there's a collision, after there's an impact. So the setup of this is I'm going to have one trolley, which is going to be placed there. It's going to travel through. It's going to collide with the second trolley and move through, and then we've got a second light gate here. So I can measure the speed before and the speed after the collision, and look for something that may be constant before and after. In science, it's about finding something that you can say is going to remain the same, because that is what allows you to make predictions after an event. Okay, so conservation laws. Stuff like the conservation of energy, or the conservation of mass, the conservation of charge. Is there something that we can find which will be conserved before and after this collision, which will allow us to work things out? But let's start with a very simple question. I'm going to have a spiky bit on this one, and I'm going to have a sort of bit that it's going to collide with. Set them up. I'm going to push this one through, and after they stick together, what do you expect, given they're the same mass, to happen to the speed? So what do you think is going to happen? What will the number be from there to there? And let's see. So what you're looking at here is the data logger, which my light gates are connected to, just so you can see the results as they come in the incredible excitement. So I'm going to turn it on, push it through, and we'll see what numbers we get. The top number will be the speed of the single trolley. The second number that comes up is the one when they have joined together. you look at that, 0.55 meters per second to start with, they join together, speed drops to 0.26 meters per second. It drops by about half, which should make sense in some ways, because this object on its own, when it's joined together, suddenly that's double the mass. The mass has increased, the speed has halved, or the velocity has halved. So that makes sense. Let's investigate some situations where we have slightly different masses. Okay, so what we're now going to do is take a result where we change the mass of these things as they collide. So the first thing I'm going to do is I'm going to add some mass to one of these. Now this on its own is 200 grams. Now adding these metal discs to it, these metal discs are 50 grams each, so the mass of this is now 300 grams. Same experiment, same idea, going to push it through, going to collide with this one, and we're going to see what happens to the velocity after the collision if we've got a heavier object sticking to a lighter one. And then what I'm going to do is I'm going to reverse it. So the heavier object will be stationary, the heavier object will be here, because I'm going to put the discs onto this one, and then I'll push it through again. And then we'll see what happens to the speeds in that sort of change of scenario. So. So the next result you're going to see is the heavier one doing the collision. So the heavier one is moving at the start. Now you're going to see a result where this one is the one we'll collide with. So here are the results that we've taken, and I'm introducing a new physical quantity. It's called momentum, and it's the product of the mass of an object multiplied by its velocity. It is a vector, so it has a momentum in a particular direction. So you have something going left or right. And it's got a unit of kilogram meters per second, because it's the product of mass, which is in kilograms, meters per second, which is velocity. So you get a unit of kilogram meters per second. And momentum is quite an important thing, because what we have is these are our results. We have the mass before the collision, which is of the single trolley, and the velocity before the collision that trolley was travelling at. And then after, we've got the mass of the two trolleys stuck together and the velocity of them when they were stuck together. And what we can do is we can look at the momentum before the collision and after the collision and see if there is something to be observed about them, which there is, because otherwise, why would I be doing this? So we can work this all out. If you want to, you can pause the video, you can sort of work these out yourselves and see if you notice something, but let's try going through that. So the other thing that's important is all of my data is collected to two significant figures, okay? So two significant figures. That is as accurate as I can write anything in these tables. I can't, although you might find that your calculator spits out large numbers, you know, that go on for a long period of time, I can't use those because I'm only confident about these to two significant figures. So all my answers are going to be the same significance. So if I put 0.2 times 0.55, I end up with a thing of 0.11. Similarly, 0.40 times 0.26 gives me 0.104, which I therefore have to say is 0.1. When I have the heavier object, so 0.3 times 0.5 gives me 0.15. 0.5 times 0.29, also to two significant figures, gives me 0.15. Here, 0.2 times 0.61, I get 0.12. And 0.5 times 0.23, wonderfully, I also get 0.1. And that is the power of calculating the momentum of something. Whenever two objects collide or interact in any way, as long as we can remove constraints like air resistance and things like that, what we find is that the momentum before the interaction is the same as the momentum afterwards. And what this means is that we can always sit there. If we know the momentum of something beforehand, so we know its mass and its velocity, and we know it's going to interact with, in some way with another object, we can work out the speed of velocity of that object after the collision. Okay, so it allows us to say, well, this number should be the same before and after your interaction. And that's the power of calculating the momentum.
Okay, so momentum is the product of the mass and the velocity of an object. So momentum okay. And what we can say from that is that this gives us the following equation, that momentum is equal to mass times velocity. And in terms of units, this is a unit of kilogram meters, not kilograms per meter second, so kilogram meters per second, and that's because mass is measured in kilograms and velocity is measured in meters per second. So we're just combining the units. We get a unit of kilogram meters per second. And that's one of the equations, which is a one to remember. Now, as a symbol, the symbol for momentum, it's weird, it's a P. That dates back to when Newton was writing Principia Mathematica. It's a P because he was writing in Latin, and it's sort of the Latin word for motion or amount of motion of something. So as symbols, it is P is equal to M times V. So yeah, it's important to get the difference between the P when it means momentum, P when it means pressure, the little weird curly P for rho, which means density. But it's, P equals mv is the way things are written. Now, that basically means that, if you know the object, an object's mass and an object's velocity, you can work out its momentum. So let's have a sort of think of why it's important. So it's important because of the conservation of momentum, which is that when objects interact via a collision, or an explosion, the total momentum before and after is the same. So momentum before and afterwards is the same. It's a conserved property, much like energy or charge and things, and that allows us to solve problems. Okay. So the conservation of momentum can be used to solve problems. So let's do a little example. Let's say we have an object, A, and we can give it a mass, let's give it a mass of 0.75 kilograms, so 750 grams, and let's say it is moving with a velocity of 1.2 meters per second. So it's going that way, and let's say it collides with object B, which I've made a little bit smaller. So let's say object B has a mass of 0.45 kilograms. We're going to say it's stationary, so we don't have any, so it's not moving at this point. And then what will happen afterwards is they are going to move off together. So they're going to stick together. And our question is going to be, how fast do they move off in that direction? What's their new speed? Now we know from having seen the experiments, we know that it's going to be moving slower. So what do we know about this so far? Well, we know the mass is equal to the sum of those masses, so that becomes 1.2 kilograms. We know the velocity is the thing we're trying to work out, and so we need to think about the momentum. So what we can say is that the momentum before is the same as momentum afterwards. So what's the momentum on the left-hand side? We've got a momentum here. The momentum of A is the product of these two, so 0.75 times 1.2. So we've got 0.9. The momentum of object B, it's not moving, so it's a number times 0. So the momentum of B is equal to 0. So our total momentum before the collision is 0.9 kilogram meter per second. Okay, so momentum now that must also equal the momentum afterwards. So what that means is that after the collision, that our momentum here must also equal 0.9 kilogram meters per second. So the velocity afterwards equals, from the equation, if we've got momentum is mass times velocity, velocity is therefore momentum divided by mass, so we get P over M, and so we get momentum 0.9 over 1.2, which equals 0.75 meters per second. And that is the velocity at which those two objects will now travel off. It's slowed down from 1.2 to 0.75 because the mass has gone up. We're going to do another example, which I'll work through. And this time I'm going to make that second object, I'm going to have it moving as well. So let's deal with the same objects and doing the same thing, but this time we're going to have object A is moving that way. So we've got a mass of 0.75 kilograms. We've got a velocity going at, let's say it's going at 1.2 kilogram meters. No, I keep getting the wrong, just 1.2 meters per second. And we already know, because it's the same as last time, that the momentum is therefore 0.9 kilogram meters per second. But now let's say that object B is also moving. Now it's got to be moving at less than 1.2 meters per second because otherwise there wouldn't be a collision, it would zoom off. So let's have it going at, so we've got its mass equals 0. What did I say it was, 45? Yep, 45. .45 kilograms. The velocity, let's say this is now moving at, let's say 0.4 meters per second. Now that gives us the momentum of this object. So the momentum of object B is 0.45 times 0.4, which gives us 0.18 kilogram meters per second. They're going to do the same thing. Now they're going to stick together. So we've now got a mass of 1.2 kilograms. Velocity is what we don't know, and we need to know their momentum. Now what you can do is, if you want to, you can pause the video, just work it through yourself, see what answer you get, and then I'll work it through. Okay, so now what we have is the total momentum must equal the sum of these individual ones. So what we get here is a total momentum this time of 1.08 kilogram meters per second, because it's 0.9 plus 0.18 gives us 1.08, and then we can do the velocity afterwards. Is momentum over mass. So we've got 1.08 over 1.2, and we get this time 0.9 meters per second. So it's moving this time a little bit faster, and that is how we can solve problems involving the conservation of momentum. And what we'll look at in future lessons is we'll start making it a little bit more complex with things going in different directions. And to summarize that, well, there's a quick little video to finish off with.
So momentum is something that is conserved before and after a collision. So we're going to make this problem slightly more complicated. What happens if these two things are moving? So we don't just have one stationary and one moving. What if they're both moving? And in fact, what if they're moving against each other? So it's a head-on collision. So what I'm going to do is I'm going to push them apart. They're going to each hit the elastic bands that are at either side, and they're going to bounce back in, and they're going to meet hopefully around here. They're going to be moving in opposite directions. And so, make a prediction. What do you expect to happen if I'm able to do it so that they have approximately the same momentum, but in opposite directions. So let's see. There we go. By moving in opposite directions, they've got opposite momentum, one positive and one negative, and when you add it together, you're going to end up with about 0, and so they stop. Near enough. Voila!